again, folks. Today we're going to cover sections 3.3 and 3.4. All right. 3.3 is the remainder of the properties of logarithms that we had started last time. And 3.4 is really this, which I have entitled Solving Logarithmic Equations. It's actually converting or solving exponential equations and or logarithmic equations. Anyhow, the handouts that would be practical to have available, or this one which you probably already have already, this is how much of the material that we had covered from last time, from section 3.2. Right. What I'm going to do now is go over section 3.3, the remainder of these. Right. Basically picking up where I had started, left off last time, rather. Change of base formula. And then I had alluded to this, which is a diagram, another diagram I had made, which is sort of a roadmap for methods as you go about the process, you know, given an exponential equation or given a logarithmic equation, what I would do, all right? If they're the same bases, if you have different bases, if you have base E specifically, and so forth. All right. There's an older handout even still, which might be useful to you because it will come up, and it's this one. Right? Some on both sides. I have my other diagram. It looks like this. It's a little bit, unfortunately, hard to see because of the light penetrating the paper, but it's this diagram. Rules for exponents. Good to have as we solve exponential equations, certainly. All right. Anyhow, those are the three diagrams that would be useful today, all right, or for this material. So let's start with this, finishing up the properties. I gotta get that out of the way. Okay, where are my glasses? There you go. I can't see without them. Right. Somewhat I can see. A little bit dirty though. Anyhow, there we are. Good to see you again. All right. Where are you? All right. I'm going to start with the very bottom one, as I mentioned, change of base formula, because I had actually left off with that, I believe, last time. This was something that was useful before the advent of the TI-8384 calculator. Or if you had some earlier incarnation of a Texas Instrument calculator. Anyhow, here is the model to start with. I use red. Do that for models. This is the change of base formula. It's starting to fade. Put that aside. Officially, it is for any base logarithm, which I'll just put as a lowercase b here, and any argument that you may see here. Argument A, base B. You can write as a ratio, like so. Right. Whatever the base is, make it the bottom one of these two. Whatever the argument is, make it the top of these two. And you may notice, I didn't specify a base here and here. That is because it could be anything that you want, right? And usually what people just gravitate towards if they're using their calculator is they'll press their log button and, you know, get it over with real quick. Which would mean it would be base 10, all right? You can do base 10. Just bear in mind, you know, it's not going to be written that way. It would just simply be written log. All right, or you could use natural logs if you would prefer. All right, if you did log of base E, Just be consistent, all right? And that would give you the value of this, whatever the base is. Whatever base log you start with, this ratio will give you the equivalent, all right? Now, the truth of the matter is, there are functions in your calculator, if you happen to have one, that you could do, that you could use. All right, let me just summarize this, if this will fit. I'll draw a diagram. Any base log, these are your options. All right, you could use this, as I mentioned, the change of base formula. Right, which is this, right? And it could be you're just using the log button, which is understood as being base 10, or you could use natural log button, which is understood as being base E. Right? Nobody bothers to write it like that, log and then base E. They just use, it's just LN. It's the equivalent, right? If on the other hand you'd rather not do that, then in the updated newer calculators, you can actually look for this function. It is entitled log and then a capital B in the middle of it, base function. All right, it's there in a modern TI-83 or 84. All right, now how do you get to it? Well, there's two ways you could if you want to. If you go through the alpha button, that may be the most practical. Alpha is usually a green button. And then press window. Let's see if that is picking up on the camera here. Green is always a nuisance. As much as I like it, it just doesn't write. And it's me is too. If you hit alpha and then the window button, you engage function 2. Right? And then it usually is something like choice number 5 is log base. Right? If, I don't know, perhaps you have an older calculator, but it still has this function, you could go through the math button. There's a button entitled math. That's appropriate, isn't it? And if you scroll down the list, there's choice A, and choice A is also log base. Right? The reason you would do that is because you won't have to type a ratio. Right? Although it is good to know that you have that as an option. What you will see instead is what will appear on your screen is a very intuitive function that has an obvious space to enter the base of your choice, and then an equally obvious place to enter as your argument. And then you hit equals and it will spit out what the decimal equivalent is. Okay, so just be aware of that. Anyhow, the change of base formula is handy, all right, if you're trying to simplify something. Perhaps you're given logs that are a ratio and they coincidentally have the same base. You can simplify them into just one logarithm rather than have two of them. So I wouldn't throw this away. I would just reserve it for practical purposes. Okay. All right. Here's an example. I may have to get a towel because I notice this is a bit hard to erase today. Let me see. Overzealous erasing will get you in trouble. Erase this now. Just for the space. Okay. let us say that you are given this. The log base 4 of 25. Right. Yes, you can enter this into your calculator, provided you have a calculator of that sort. The software is updated, or you could take advantage of the change of base formula. So, if this is the base, make that the bottom one. Basically, the base here becomes the argument as a denominator, if you will. Right. What is the argument here? Make that the top one. And then you would have log of 25 over log of 4. You could, if you want to, make any base that you want here, but the whole point of this is to be able to use your calculator. So just if you can, you have a button that is designated log, all right? It is understood as being base 10 without having to dwell upon it too much. Now, here's what you would get if you used your calculator. All right? There's no settings or anything that you have to change. Let me turn on the light. That helps a little bit, somewhat. Okay. Log button is here, and there's natural log there. If I turn on my calculator would help. There you go. Okay, so we would type log 25, obviously. No, I'm typing it backwards. And then divide. And then log again. And then 4 in this case. You would have it written intuitively or typed. And I hit the wrong button, so I'm reading it backwards again. Okay. Come on, what am I doing? I'm hitting enter. Need to hit enter. There you go. 2.3219, whatever it is, into infinity. Now you could basically round this, right, to whatever number of decimal places that is predetermined, or I would say go 3 decimal places in for a good degree of precision. Anyhow, you would have something like this. 2.3219 something into infinity, about 2.322, Okay, so not too difficult, right? Even if you use natural logs instead of going this route, you went this route. You use natural log, which is base E. As long as you put these figures, 25 and 4 respectively, in the appropriate places, 25 would be on top and 4 would be on the bottom, you should get the exact same decimal. Now, as proof of that, I'll do it real quick. So you went for natural log, right? 25 division natural log of 4, close the parentheses, hit enter. There you have it. 2.3219, so forth into infinity. It doesn't matter what base you're using, as long as they are the same bases here and here, which is why in the formula they will usually just put a little subscript n. Okay? Useful. Okay. Anyhow, being that logarithms are the inverses of exponential functions, it makes sense that there would be corresponding properties. So, for example, right, we've had a long time ago a product rule for exponents. We had a power rule and a quotient rule. There are others as well, but those 3 are very handy. Right? Well, again, if logarithms are the inverse of exponents, then it would make sense that they would have their own rules as well, properties, right? And that is what the other half of this is, right? I covered the bottom one first, but let's discuss the effects of these. The product rule, the quotient rule, and the power rule, right? Think of them as basically alternative ways of writing something. I put them in 2 different colors on my sheet here. I put them in purple because you often see them presented to you this way. And this is what they would translate to, if you were going to expand them at least. There are some cases when you would write these sort of backwards, in which case they would call that condensing instead. Right. Let me get paper towels. This isn't going to erase nicely. Precarious, but okay. Years ago, I used to stock pickles at the A&P, and I can't help but sense that they gave me that job because nobody else wanted to do it. Because they're very easy to break pickle jars. I just left my little squirt bottle on the ledge of the window here, and I couldn't help but be reminded of that somehow. And it was about to fall. Hopefully it won't. If you hear any sudden thud or crash, you'll know what it was. My negligence. That is a little bit better. Alcohol cleans these acrylic plastic a little bit better. And even the brand that came with the markers. Yeah, it's unfortunately not perfect, but it'll do. Put this here now. Don't get dirty. Okay, so here's kind of an overview of the process of simplifying, you might say. Sometimes you get vague instructions and it just says, well, simplify. Right, what does that mean? Insofar as logarithms are concerned, right, there's really two ways you can go about it. And they are arguably simplified in either respect, right? One is to expand the expression that is given to you, stretch it out so that you can see more clearly, you can simplify in certain context, what the thing is made of. Or you can condense a big, long expression, right? Maybe several terms long, or several factors, right? You can condense it into something else. In the context of simplifying, it is arguably simplified because you've shortened it. Condense, like soup. Okay. Now a couple of things. You may start with something that is expanded, in which case they say simplify, they mean condense it into one term. Or you may start with something that's kind of crushed together, that is condensed already, and they say simplify, in which case they mean expand it. Show all of the individual parts that it's made out of, right? An exploded view, if you will, like in an engineering diagram. Right. Anyhow, if you're given this, then do this. Condense. Right? If you're given this, then do this. Expand. How to do that? Well, properties. Right? Use properties in order to accomplish that. All right, I would say in the case of condensing, be a little extra careful about. All right, in order to combine things, legally speaking, to combine logs, they must be the same base. If you see that they're two different bases, it may be possible in theory to convert them to a common base, but if they're not the same base to begin with, don't try to condense them. Okay, they'll just be standing next to each other, more or less. Okay, now let's go through this. examples here. It's my eraser, I think, is the culprit. It's making it so difficult to erase. All right. It's gonna be difficult, huh? Okay. Try not to do this. I think I will this time. Maybe if I clean my eraser, I won't have such a problem. Yeah, that's the ticket. Okay. I'm gonna have to wash this. I mean the eraser itself. But I'll do that later. How much time do I waste just cleaning stuff like this? Too much. Back to work. Here's an example of simplifying by expanding. If you were given the natural log of 6, right, and though in your textbook as you do the problems, they have a tendency, for whatever reason, not to put things in parentheses, I would. All right, whatever is the argument, that is the number or factor or term or letter, whatever have you, that is adjacent on the right side of the function, I would put in parentheses to go, okay, this is the argument. This is the thing that is the input value for the function. Anyhow, what you might try to do is basically factor the argument of the function, which usually means into primes. Remember prime numbers 2, 3, 5, 7, 11, 13, things like that. They only have 2 factors, one in itself, one in itself, one in itself. So in the case of 6, what can you factor it into? If you used 1 and 6, right, you wouldn't really be making much progress because you'd still have the number 6, but you can factor 6 into slightly smaller numbers, the primes. So 2 and 3, right? Still inside the argument, still part of the function that is the natural log, base e. Right. Now, once you have done that, right, notice this, right? As for your logarithmic properties, I'm going to fold this in here. It's a little bit hard to see. Yeah. You have, as you have a product rule for exponents, you have a product rule for logarithms. Okay. If you have factors in the argument, right, you could write them as a sum. Similarly, for the quotient rule, if you have factors in an argument that are stacked, as if they were a fraction, if divided, then you could write them as a difference. And then there's the power rule. If you have an argument that's raised to an exponent, you could write the exponent out in front. That's the gist of basically these 3. And the one that is going on here is the product rule. The one that would be useful here. So, if you have identified your 2 factors, that is factored into primes, then you have the natural log of 2 by itself plus the natural log of 3 by itself. Right? And if you're a little bit sketchy about, well, does that really make the same thing that looks drastically different? Sure enough, if you enter this into a calculator, log of 6, you will get a decimal that is equivalent to these, the sum of these 2. Right? Here's proof. The natural log of 6 and the natural log of 2 plus the natural log of 3. 1.79, 1.79. It's legit. Too legit to quit. Okay. Here's another one. There goes my paper towels. Okay. Suppose you had this to start with. the natural log of 2 over 27. Right. Again, I would go about the process of expanding it as to factor it into primes. The prime factorization of whatever numbers you can. The number 2 is already prime, but put this in a different color. The number 27 is not prime, it is a composite. So what can you factor 27 into? Well, you start with two numbers, 3 and 9. 9 is prime, but, pardon me, 3 is prime, but 9 isn't. So you would factor 9 into 3's, right? And the bottom rung of this factor tree would be the prime factorization. So in theory, it would look like this, at least to start. Okay. Now, there's an alternative way of writing this as well. Remember, when you have multiple iterations, clones if you will, of some base number, in this case the base number is 3, right? You could use the abbreviation of an exponent. So the next step would potentially be this. The natural log of 2 over 3 squared. Okay. Now at this point, there really isn't anything else you could do with them together. So now you can take advantage of properties of logarithms. And in this case, it is the quotient rule, which again says that if you have an argument that is a ratio, right, you could break it into a difference, right? Just maintain the same base, whatever the base is. It's a natural log, so it would be base E, but you don't have to worry about it. The effect here is this. The top is written first, so it will be the natural log of 2 minus the natural log of 3 squared. There is one last thing that you can do, which is take advantage of the power rule. The power rule indicates that when you have an argument that is being raised to an exponent somehow, that you could write it as a product of the regular log and that exponent out in front. It's a coefficient, if you will. So that means you could park this up in the front, right? And therefore this would be your outcome. The log of 2, pardon me, the natural log of 2 minus 2 times the natural log of 3. That would be expanded in its most simplistic way. I'm mixing too many chemicals here. If I start to get a little dizzy, you don't know why. So I'm mixing Windex with whatever proprietary blend this is, all right, and isopropyl alcohol, 91%. So what is the word, that old phrase? I conform to a higher standard, 91%. I may need to open a window, it's getting a little intoxicating. Yeah, everybody, it's time for logarithms. Hiccup. Okay. Okay, back to reality here. A lot of times they will ask you to, as much as it is unsatisfying, get the exact answer. All right. One thing you will notice is that a calculator is great, right? And the past couple of problems, you know, we would have very high degrees of precision, right? I believe that's like 10 decimal places, right? Which is great. But these are irrational numbers if they're dealing with E, you know. So you would have to chop off infinity at some point by rounding, right? Which is not great. You know, ideally, and you'll notice this as you go into upper level math calculus and behind that, preference is not to use a decimal number, even though that's what we have all been conditioned to do since little children. The calculator is God, right? It's not, all right? We can craft basically an exact answer, and even though we're kind of fighting our intuition when we get the end result, we go, oh, it's not done yet until I ask the calculator what the decimal is. It's a better answer what you may get if you get an exact answer. So let's look at that. Here, if the instruction is find the exact answer, it may be counterintuitive, right? But it is a better answer. This means, you know, without a calculator. Squeaky. Okay. So if you had the log of base 5 of this radical expression, the cube root of 5, just coincidentally. Right. What you can do is, again, take advantage of properties, right? There is one older sort of trick I would pull here, which is to convert something that happens to be in radical notation. I would convert consciously, intentionally, to rational notation, which is more or less to write the base with an exponent that is a fraction instead, right? Whatever the index is, that's the denominator. That is, whatever type of radical it is, in this case it's a cube root, it'll be a denominator of 3, so the exponent will have a third as a denominator. That means that our fifth here, our cube root of 5 can be rewritten like so. Still log base 5, but it would be 5 to the 1/3, all right? Because that's what the index is, and if it's not written, one would assume the exponent on the inside here is 1. Right. Now what? Well, what you can do is take advantage of the power rule. Which means that if you have an exponent here, you could write it as a coefficient. Okay. And then you have this, 1/3 up in front. At the exact same time, you have this. You have a log that is base 5 that now has an argument of just 5. All right. There is a property that has been established already, all right, that says that if you have this, that basically you're dealing with inverses. So I will point to that. Here. When you have a logarithm, whatever the base is, that happens to be the same as the argument, the outcome is 1. That's the only thing that would establish this as being true, that if this other side of equals were 1. So this expression that you have here, of log base 5 of the argument 5 is really just 1. So if it's 1/3 times 1, that means that the value is really just 1/3, right? Which is what? 0.33333 forever and ever and ever and ever. An irrational number. Well, it's not irrational, it's rational, truly, it came from a fraction. But it's infinitely repeating, right? It's a repeating decimal. So better to have the fraction that summarizes all of infinity rather than simply chop off a decimal. It is preferred to have a fraction, believe it or not. Okay. Rational. Sometimes rational numbers are a pain in the neck too, and they repeat. All right. Underneath the this property that we have applied here that is nameless is the inverse property, right? which is basically a summary of what just happened here. When I had an exponent, it would really be left over. Why? Because of the situation above here. These are inverses, all right? B to the 1 and a logarithm of b. So if you have 1 times whatever the exponent written in the style of a coefficient, that's the power rule down here, this would be the only logical outcome. Whatever the exponent is, that becomes the outcome. Okay. All right, now let's do the opposite of expanding, or finding exact values in this case. Let's do the opposite of expanding, which is to condense. Start with something that is stretched out already. Right. And we'll take advantage of properties to do that. I'm going to try one more fluid, all right, to erase this, which I think will have to be Windex. Good. The alcohol works better. Oh man, it's getting bad. Blue is extra sticky today. Maybe I should just bite the bullet and buy a white one. I'm sorry about the intermission, as I often am subject to here. Alcohol does it, Windex fails. I'll figure. Some of the perfection of this later, but not right now. Okay, dry. Yeah, okay. Let's do this. Let's say that you are tasked with condensing. Simplifying in a certain context. You are taking something long and complicating and combining it into one expression, if you can help it. So, if you had the natural log of e to the 6 minus the natural log of e to the 2, all right? As long as they are the same bases, then you can combine them into one expression. This is becoming a dud. Okay. So, we had been using the quotient rule before to write differences. What if you had something that already was a difference? That means that you could take this and write this as 1 natural log, e to the 6 over e to the 2. Right? Incidentally, there's probably more than one way to go about doing this, but this is the way that it occurred to me, which is to combine them, just seeing that subtraction symbol right off the bat. Anyhow, when you have like bases, as you would, they happen to be e's in this case, you may remember from a while back, and this is why I said have this older document handy, that, I'll fold this in half. According to the quotient rule, when you have the same bases, one sitting on top of the other, a quotient, then you can subtract the exponents and write them with that abbreviation, whatever the difference is. So that's what I would do here, right? According to the quotient rule for exponents, I can subtract these, which means that the next logical step here is that this is the natural log of e to the fourth. And then you could take advantage of the power rule. Alright, which means that if you have an exponent here, you could make it coefficients, if you will, up in front of the function. So you then have 4 times the log of e. These happen to be inverses of one another. It's a little disguised. If maybe you had it written in the more traditional log form, I'll just write it like that now. This is not necessary. If you had a natural log, it would be base e. Right? And if the argument and the base happen to be the same thing, you already know they're inverses. All right, so the effect is that this is just the number 1, which means that 4 times 1 is just 4. That is the outcome. Okay. All right, let's do a couple of these back and forth. Hopefully this erases. It's not working out so great. What have I done? Oh, that's horrible. It's cleaning my eraser, then great. That's terrible. Thanks. I have to get another piece of paper towel. I'm sorry. Oh, that's horrible. At this rate, I'm not going to have any paper towels left. I don't know why this is being so utterly defiant today. Let's see. How far can I go with that? Don't bother. All right. Yeah, no alcohol either. All right, that's a little bit better. Oh, the fail. One after another today. I'm sorry. I'm gonna throw that eraser out. It's just trouble. Or at least wash it. Deep scrub. Ugh, so horrible. This one now? Looking through itself on the floor in shame. I mean, you better be embarrassed. It's holding inanimate objects now. Ugh. Working in a coal mine, working in a coal mine. Alright. Nope, still horrible. Okay. Ugh. It's probably not a good idea to mix, as I said, the various chemicals that I have here. It just so happens that alcohol works fast. This 800 times today. I'm gonna put this away because it's causing more trouble than it's worth. As well, I'm going to take this eraser and throw it in the sink. Be gone, Timon. That's enough of that. Let's get busy. Here's another example of expanding. I don't know why the book decided to do this in this order, but okay. Expand. The log of base 4, and the argument is 5x, multiple factors here. 5x cubed y. Okay. All right, now, if again you're utilizing the properties here, 6, 7, and 8 as I labeled them, product rule, quotient rule, power rule, predominantly. Start by factoring. And what does that really mean? It means separating these things out with dots. So 5 dot x cubed dot y. In terms of this particular expression here, that is as much factoring as anybody could do right off the bat. Right. Make sure that this is in the frame. It looks like it is. Okay, cool. Right. Now, according to the product rule, we can basically break this up into sums. Right? The rule base 4. So it'll be log base 4 of 5 plus log base 4 of x cubed plus the log base 4 of y. And the only other thing that you can do is take advantage of the power rule in this case, which is to say, okay, there's an exponent, I'm going to park it up in the front. So the end result is this. Log base 4 of the argument 5 plus 3 times the log of base 4 of x plus the log base 4 of y. And there's nothing else that you can do with it insofar as expanding is concerned. That is completely ripped apart. Okay. Let me see if I could squeak in another one over here without having to erase, because that is always catastrophic for me. All right. So I'll do this over here. Suppose that you had the natural log of the expression the square root of 3x minus 5 sitting on top of 7. Okay. And both of these are underneath the radical symbol, so I really should do that. Okay. This is a quotient, all right? So as long as you convince yourself when you see a line that this is a quotient, to take advantage of the quotient rule, which says that you'll break them into a difference in this case. 3x minus 5 minus the natural log of 7. Right? Regular ordinary number 7, can't do anything else with it. This one you could dress it up a little bit. All right. I would, again, in this instance, it predates the subject of logarithms, but convert this from what it is. It's radical notation into rational, which is basically to give it an exponent that is a fraction. So if this is a square root, right, although the index is never written really, it would be a 2. Right? And the inside guts here would be exponent of 1 because it doesn't have anything. So you assume it's 1. That means that this is the natural log of 3x minus 5 to the 1/2. Right? Minus the natural log of 7. And again, according to the power rule, there isn't anything else you can do with this except to sort of write this up in the front. So you would end up with 1/2 the natural log of 3x minus 5 minus the natural log of 7. You might wonder, well, there's two terms in here. Is there anything else that I can do with it? No, sadly you can't, because they're part of the argument. All right, they're not factors. All right, factors are things that are being multiplied. These are merely terms, you might say, and terms that are inside the argument you're stuck with. Okay. Let's try another round of condensing here. Geez, that worked a lot better, didn't it? Not spraying it. I'll figure. Green is still problematic. Okay. There's a bit better. Let's condense again. Suppose you would have started with 1/2 the log of x. And adjacent to it is the term 3 log of x plus 1. Again, there may be multiple ways to do a problem. This is just the way it occurred to me. Alright, bear in mind, alright, these are the same bases, alright, which means that it's okay to combine. If they were different bases, perhaps you could do something, convert them to exponential form and then merge the two, but otherwise not, right? They're okay to combine because they are the same bases. And they have a plus in between them, right? So we're going to use the product rule. What you might do first is sort of reverse the power rule. You notice that there is a coefficient up in the front here. So the power rule says that if you had an exponent, that you could make it a coefficient. What I'm going to do is I'm going to put it back, so that you have the log of x to the 1/2. And then the same thing here with this 3. Make this cubed. X plus 1 cubed. And now, maybe take advantage of the power rule. Right? Pardon me, reverse the product rule. So, plus, they're the same base type. If there is no number written there, you would have to assume it is base 10. You don't have to write that. You could just write log. Right. The thing that is in front of the plus, that goes in front in here. I'm going to separate them by dots just for right now. And then the argument here, x plus 1 cubed. If you feel more comfortable, opt for a different style of parentheses, perhaps a bracket, just not to confuse how things are grouped. It'd be like so. One more thing you could do is the opposite of this process. I'm starting with something that technically is in rational notation here. So what I could do is go backward, convert this to radical notation in this case, which means that this is the log of the square root of x sitting in front of, I'll put this in red to make it more distinct. And they'll fade now on me. X plus 1 cubed, kind of stuck with that one. And then close this parentheses. Okay. That would be the end result down here. The log of the, it's technically base 10, but you could just say log of the square root of x times the quantity x plus 1 cubed. Okay. And that's it. Okay for that. Two more of these and then shift gears here. I'm trying to cover all bases, make sure that you see everything. Let's see. Let's do this one. Okay. That's not gonna fit. This is probably about as hairy as it's gonna get. Still condensing, we'll do this. 1/3 times the quantity of the log base 2 of x, plus log base 2 of x plus 1. Okay. Again, just be anal. Pay attention to what the bases are. They are the same, so you can legally combine them into one expression. Let's get all. In which case, what would you write? There are some, so therefore the product rule would be most appropriate rather than the quotient rule. If you saw a minus here instead, then you use the quotient rule and you stack them. Anyhow, this would simplify to the log base 2 of these two arguments as factors. I'm going to group them like so. Okay. I like to use multiplication dots just to kind of get adjusted first. If you want, you can also opt for brackets, just not to confuse how these things are grouped. Make it a little bit more obvious. And meanwhile, there's still this 3 here. Right. Now at this point, this is more or less reversing the product rule. What we're going to do in this case is reverse the power rule. If there's a coefficient up in front, you could make this an exponent instead. And that would make this log base 2 of the quantity x times x plus 1 to the 1/3. Right. And the last thing you could do is, again, switch from rational notation, where you have an exponent that is a fraction, and then write it in radical style. So whatever the denominator is, that's the type of radical. So if it's a 3, you would assume it is a cube root. Let me put this just here. The end result would be this. Taking this and converting it like so. The log base 2 of the cube root of these quantities. And technically there would be a 1 here inside like that, but it is an option that you don't need. Okay. Now you might wonder, should I distribute these? It isn't wrong if you do, but that would be fine, right? I think in most cases. In other words, you wrote x squared plus x. I don't think there's anything wrong with that. Nothing wrong with that at all. Okay. Okay. I'm debating whether I should tell you something. Let me bite my tongue for a minute and move on. Okay. All right. Now on to section 3.4. here again is where this roadmap would become useful. All right? We're going to have equations now and logarithms, and we're going to convert a lot of times back and forth between the two if it's a convenience for us. All right? Or take one of these paths. All right? If you're given something that is an exponential equation, if they're the same bases, right, then you would say that they're 1 to 1. And the only thing that you really need to pay attention to are the exponents themselves, right? If the bases are the same, all right, then just make a little tiny equation that involves the exponents only, right? There is similarly a 1 to 1 property for logarithms. When the logarithms are the same bases on opposite sides of equals, then you could write a smaller equation that involves just the arguments. So whatever the argument is on the right side, set it equal to the argument on the left side. And it may involve more steps than just saying that, all right? But that's where you would have, that would really be the equation, okay? You could alternatively take a graphing calculator and graph both sides of your equation and then look for the point of intersection. That would work in both cases. But that doesn't come up too much in your homework because they assume you don't have a graphing calculator. Okay? Now, let's see. I can erase in one step here would be great. Dreadful. Is it legible? Yeah, looks like it's okay. Okay. All right, let's take advantage of 1 to 1 first. This is, mind you, the beginnings of section 3.4. Proper. All right. So we're going to discuss this concept of 1 to 1, which is true, basically a property that you could take advantage of in both cases, whether you're given something exponential to start with, or you're given something logarithmic to start with. I did allude to this a little bit earlier in the handout for properties. There is a 1 to 1 property established here. Okay? If you have logs on both sides of your equation, then you could just pay attention to the arguments, basically. And if you have exponents with the same bases, just pay attention to their exponents. Okay, so this works for exponents with the same base, or logarithms with the same base. Here and here. In the case of exponents, let's say hypothetically that you have this. 2x is equal to 32. All right. The trick to a problem like this is that you should try to convert to a common base first. That doesn't always work, all right? But if it does, and it will in this case, all right, then you could use 1 to 1 property. the case of 32 could be written as 2 to the 5th. So if what you end up with is they're the same bases on opposite sides of equals, all right, then the only thing that you really need to pay attention to are the exponents. They would be 1 to 1. And you would have a smaller equation, which is really just whatever is written here, x is equal to whatever is written here, 5. It could be something more complicated than just the letter on the left side and the number on the right side, in which case you would just go through the process more or less algebraically. But that is the principle. Matching bases, just pay attention to the exponents. Okay. Let's do another. I have to dig up the numerator. All right, here's a logarithmic example. If you had the natural log of x minus the natural log of 3, and on the opposite side it's set equal to 0. As in the case of regular traditional algebraic equation, you would want to try to isolate the variable. And in this case, the variable is part of the argument over here. So I have to sneeze, forgive me. I'm sorry. I'm allergic to myself. Anyhow, if you're gonna, as you normally would in the case of an algebraic equation, start to shift things over equals, all right, for the sake of getting the letter on one side. It's unfortunate that the letter is sort of encapsulated right now, but we can take care of that later. What we need to do is just more or less move this to the opposite side. And the way that we would do that is exactly as we had done with algebraic equations. All right? These are transcendental, so what? They still conform to the older set of rules. The opposite of subtracting the natural log is to add it. That would justify moving it. And on this side, it would be positive instead, right? Whatever the quantity of the natural log of 3, regardless, combined with its opposite sign self would cancel out of existence. Okay? And then you would be left with this. The natural log of x is equal to the natural log of 3, because combined with 0, it isn't going to change naturally. Right? Now you have the situation that is ideal. You have the same bases, it's disguised because remember it's a natural log. That means that it's base e and base e. You have the same bases on opposite sides of equals. So we could take advantage of 1 to 1. Right? For the sake of logarithms, what you would just pay attention to exclusively is the arguments. Right? This is the equation that would result. Just the argument on the left and the argument on the right set equal to each other. If it was more complicated than x, then you would perform more steps algebraically, but it isn't necessary in this case. It's just x is equal to 3. Okay, that is that in a nutshell. Full 1 to 1. Let me see if I can get another eraser, because this is really dreadful. Water would probably work. Let's see. Forgive me. Right back. Get this. doing part-time in the sink. I think it's time to restore my poor razor to its former glory. Hopefully it'll work. I washed it, so it's a little bit better. At least it's not spreading its muck around. It's just a hint damp, which is great because it cleans without having to use alcohol over and over again. The only downside to this is that I'm going to have to probably wipe the board frequently just to make it dry. Nonetheless, I won't pass out from the fumes, nor sneeze anymore. Yay, that works. I'll do this. Really. Good. Fantastic. All right, now more examples here. I just have to reintroduce new markers here. So, all right, dry. To dry. No wet surfaces, please. Don't run on the wall. Okay. My landlord is going to kill me because the fuss that I've spread all over, not just my board here, but on the wall behind it. Don't tell him, okay? I'll be evicted. That's what will happen. Okay. Once again, we're confronted with a situation of, well, let's decide what type of equation we have. There's no word log written into this at all. So out of my methods for addressing this, right, it may end up being 1-to-1, but let me just show you how I would use this map. Decide up front, do I have an exponential equation or do I have a logarithmic equation? I would argue that this is exponential because you see an obvious exponent where the variable is. There's no word log written into it. So pay attention to this half of the map here, all right? This is an option that you always have, right? If you had a graphing calculator, you could set this equal to y1 and this equal to y2, and then superimpose the graphs and look for the point of intersection, and that in theory would be the answer for x. But let's do this algebraically. Are you given the same bases, right? As of right now, no, we're not. But it might be possible, all right, to convert these things to the same bases. And if they are, then we're going to take advantage of 1-to-1, all right? So let's try that. All right, if you were, basically this is what's happening here. If you were given different bases, attempt to translate into a common base. Use rules of exponents. What are the rules of exponents? These again, okay? The negative exponent rule for exponents is probably going to come into play here. So, let's see. It's also good to know your multiplication tables at this point as well, because you may recognize that there's a relationship between these. I'm going to take advantage of negative rule for exponents and see if I can translate this. If this is a denominator, and although it's not written, this is an exponent of 1, all right? If I were to grab this and basically move it to the top so that it's on the same tier, at least, as what 9 is. 9 is technically a top, not a bottom, all right? Then this would be 3 to the negative 1. Right, just making that one alteration. There is still this x that is sitting outside here, and there's still this 9 here, right? But now, still taking advantage of, again, rules of exponents, right? The power rule would come into play, where I have an exponent raised to an exponent. I'm sorry for the light bleeding through my paper. When you have an exponent raised to an exponent, according to the power rule, you actually multiply them. You would multiply these, right? In which case you would have this thing. You would have 3 to the negative x. You could put a 1 if you like, but the parentheses here would now no longer be necessary. and then there's this 9 here. All right? Is it possible to translate 9 into a common base? I would. The number 9 can be translated into 3 to a certain exponent. All right? 3 to what exponent would produce 9? 2, right? So, at this point, it is now 1 to 1. Because you have the same bases for the exponents, the only thing that you really need to pay attention to are the exponents themselves, and that becomes its own little teeny tiny equation. You would have negative x is equal to 2, which means that if you rearranged it for the negative, it would be just x is equal to negative 2, and that would be your answer for x. Okay. All right. Let's see. All right, let's discuss inverses. Get through this. I'll clean it first. Blue writes very well, but it's not going away. Maybe it's the soap. Paper towel. It's getting too wet. Here, this will be an issue of inverses, what you can do to take advantage. Okay, suppose you had e to the x is equal to 7. All right. Now in this case, you really can't apply the one-to-one relationship property because there's no way that you can convert these into the same bases. This is a base 7 to start with. This is a base E. All right. So as for the roadmap again, what you might do when you're given different bases, if you can't, when you're given different bases, if you can't do this, if you can't convert to a common base, then what you might do is apply logarithms. All right. You could apply common log, right? If 10 is somehow already involved, that would be practical. You could use natural log if e is somehow already involved, right? I also wrote this as a reference here. If you have base e to begin with, and you take the natural log of it, you're gonna get 1, all right? Because they're inverses. But let's see. If I took the natural log of e to the x, I would be obligated, as I often am in algebraic equations, to do it to both sides. Right? That's what makes it legal. If I did it here, really for the sake of employing an inverse, for the sake of some kind of cancellation, all right, I must do it to the opposite side. Right? Somehow I got bit by something. I'm sorry. All right. Anyhow. According to our inverse properties, which is on that sheet, this is really, I don't want to drive you nuts, but this is really a log base e. What happens when you have, all right, a log base e and the argument is the exact same thing? It really is just 1. This becomes 1 by itself, all right? All right. Now, one of the formalized explanations I have here for inverse property is this, all right? When you have an exponent involved here as well, that's really 1 to the exponent here. You can write this, right, as x, all right, whatever the exponent is. Alternatively, if you employ the power rule first, you might notice that the exponent becomes the coefficient before that, all right? This is really saying the same thing. The power rule would have this up in the front. All right. If this natural log of e is really this situation, then it's really just going to be x that got moved according to the power rule times 1. All right, which means that this is really just what? X. And then you have the natural log of 7, right? Which, that's exact, all right? If you want to, you can type it into your calculator, and if they specify around it to so many decimal places, cool, but this is an exact answer, so that's really ideal, all right? X is isolated, x is equal to the natural log of 7, it's just a number, it's a real decimal number. I'll do another one adjacent here. Just not to have to erase it so much. Okay. If you had the natural log of x to start with, right, is equal to -3. Right? Let's see. There's a couple of different ways, as is often the case, of doing this. What again I would try to convince myself of is deciding what type of equation you are given, all right, for the sake of using the map that I made. You started with an exponential equation, so you applied a logarithm to it, all right? In this case, you're starting with a logarithmic equation, all right? It's a natural log specifically. So just to point to this, all right? If you are starting with a logarithmic equation, again, you could graph this if you want. You could try 1-to-1 if they happen to match on both sides. They don't in this case. Or this. If you're given some kind of logarithm, it's natural in this case, equals a number on the opposite side, or whatever is here. All right? Attempt to translate into an exponential equation. Right? All right? How so? All right? You could apply properties of logarithms. All right? In particular, the inverse property is very practical. If you have log of x, all right, I would go with applying 10 to this. If you have a natural log, which is a base e, I would apply an e to this. Those are the inverse properties, respectively. So, if you basically convert this from what it is, a logarithmic equation, into an exponential equation. Right? The most practical way to go about that is to remember that this is a log of base e, really. Right? Raise this, we'll give it the base of e so that you could take advantage of inverse properties. And if you did it here, right, make sure that you do it here as well, to both sides of equals, to make it balanced, right? Be consistent, right? Do to both sides. Okay. What is going to happen here, all right? I'm driving myself crazy moving papers around, but yeah, let me show you. This is an example of the inverse property. All right. Inverse property 2 is how I have it labeled here. When you have some base that is the same base as this logarithm, all right, the argument is the outcome. So this will simplify to what you see in red here. All right. It's kind of this backwards, you know. Anyhow. So just match the bases. If this happens to be a base e because it was a natural log, then raise it with a base of e here. All right, that's that. All right. The result is that this is just x is equal to x to the is equal to e to the -3rd. Now, if you feel a little sketchy about that, there is no alternative way of doing that. And I'll show you. It might be a little bit more self-explanatory, so I'll draw it next to it here. This is the same problem, just done in perhaps a more intuitive fashion. It's up to you, you decide. Okay. I have to be careful about this. Okay, that's good. If this is the same problem, just done a little bit differently, and you again take it into consideration, well, when you have a natural log that is the same as if you had base e like so, what you can do is what I had instructed you to do earlier, right, when you're converting between these, which is, silly as it may sound, draw the jelly bean. What do I mean by that? I mean draw with this, when you're converting from logarithmic form to exponential form, right? You connect these two things on opposite sides naturally of the exponent anyhow, which means that this is really, and you read counterclockwise. You write this as e to the -3, and what does it equal? It equals whatever's sitting in the argument here, which happens to be x. And that just kind of gets you to the answer without employing any properties. It's just converting from one form to another. Right. Anyhow, this is the inverse justification for why you get this. It doesn't matter if the x, the variable, is on the right side or the left side of equals. Right? It's the same result. Okay. Let's see. Stubborn man. I don't know why. There's always one color, and it's always a pain in the neck. It's usually green, but I think blue. It just won't go away. Suppose you started with this. The log of x is equal to -1. Again, decide what type of equation that you have. If you see the word log, it's a logarithmic equation, no bones about it. And again, just to show you how I constructed this map once again, all right, you pick sides here. Am I working with something that starts as exponential or logarithmic? In this case, it is starting as logarithmic. So I'm going to focus over here, all right? If you were given this scenario of a log equal to a number, again, you're going to attempt to translate into an exponential equation, right? Apply properties of logarithms. This is more or less this situation where you have, I should have added this rather than wrote it, a log of x. It's understood as being base 10. So if you're going to raise it to something, because if you want to employ the inverse property, use 10. All right. So if you have to fill in information, that's really what it is understood to be. Like square roots is really an index of 2. So if I purposely raise this to base 10, and this is what you see here, just do the same thing to the opposite side. Whatever you do to the left of equals, do to the right side. That's what makes it legal. Okay? These are now inverses. And the result that you get x, okay? All right, now as for this is an older rule, the negative exponent rule, which says that this is really a fraction of 1/10, right? Again, if you do it more or less the jelly bean way, right, you're gonna get the same answer. Here's what would happen. I'll tweak this slightly. It's not a permanent marker. No, it's not. Came in the same package as the rest of them. Okay. Incredible. Okay. If this is the same problem, log of x is equal to -1, and you just fill in the missing information, and you convince yourself that this is real. If it's just log, that it really is base 10. Then again, draw the jelly bean, right? Which means that is a jelly bean, right? Arguably, or a lima bean in this case. All right, delicious, right? Yum. And you link these things together, and you read counterclockwise. So this would be 10 to the -1 is equal to whatever is in the argument here, which is x. It's the same answer, all right? It's just now taking advantage of the fact that it is a negative exponent, so what is that? 1/10. Okay. Let me speed this up a bit. And now please take advantage of this. I mean, I tried to make it as useful as possible. The only thing I neglected to do is when I typed this is that I neglected to give you these two examples on the bottom of this one. Okay? There's appearance that I'm going to need this many, many times. I don't know why it wasn't like that a couple of days ago, but whatever will be, will be. Okay. Here's another one real quick. You are given the log base 3 of x is equal to 4. All right, again, if you are given something that is a logarithmic equation, all right, look at the logarithmic side of the diagram, but ultimately try to convert it to an exponential equation. All right, and the easiest thing to do, all right, is to just do this. You know, draw the jelly bean. All right, it's 3 to the 4th is equal to x. All right, you always read counterclockwise. Whatever's in the argument is the opposite side of equals. Right, now what's 3 to the 4th? It's 3 times 3 times 3 times 3, which is really 9 times 9, which which is what? 81. X is equal to 81. Let's see. Here's another one. If you're given e to the negative x squared is equal to e to the negative 3x minus 4. Don't be intimidated, all right? It's ugly, all right, certainly. But again, get in the habit of assuming that there is a way to do it. It's not impossible, all right? And that you have a roadmap and that you just need to pick which of the paths of the trains of thought are appropriate. These are e's, granted, but are they the same bases? They are the same bases, right? So what could you say for certain? They are 1 to 1, right? Which means that the only thing that you really need to pay attention to is the tops here. And it's awful because you have a lot of stuff going on, but this is really the equation that you reduce it to, right? Can you employ some other technique? Could you apply a natural log here and to here? Yeah, all right, that would work too, but it's a more intricate justification for it, but it's not necessary. It is definitely 1 to 1. So you have this equation, right? You may recognize at this point, well, geez, you know, that is an exponent of 2. So this is quadratic. All right? I could just manipulate it by moving things over equals. All right? If I were to say strategically move the negative x squared over to the opposite side, I would do so by adding, and I have no place to really plop it, so I'm just going to put it here. There would be a cancellation effect, and the void would be filled with 0. Equals. I'm going to put this, I'm going to be conform to quadratic. I'm going to put this in descending order. So the highest degree term, which is x squared, will be in front, minus 3x minus 4. All right. Now at this point, I would take advantage of the established techniques that I have for solving quadratic equations, which is really all that we have now. Which is to say, okay, I'm going to rearrange it so that it is in set equal to 0. I'm biting my tongue and trying to say not general or standard because there is a discrepancy. Right? Standard in the context of functions is not the same thing as standard in the context of a general equation here. So anyhow, don't dwell upon it. It's 0 equals this quadratic. So I'm going to try now to factor. And you don't have to really go into any super duper techniques here. All right, it's pretty basic type. The coefficient is 1, so that means it would be x and x, right? And if you consider the factors that make 4, it's either 1 and 4 or it's 2 and 2. The appropriate choice would be the one that also makes 3, if you maybe add or maybe subtract. So I'm going to go with 4 and 1, right? And then I'm going to sort of talk myself through the process. These are going from something arguably larger to something smaller. So if I have two choices, adding or subtracting, which one makes things smaller? Subtracting. Now, what causes subtraction? One of each sign, meaning one thing is positive and one thing is negative. If I want the outcome to be negative, the larger magnitude has to be negative. And that would be that. Then you take advantage of the 0 product rule, which says that, well, if these things are equal to 0 and they're factors, they're isolated, so they're factors, then that means that either one of these potentially could be 0. Maybe that chunk, maybe that one, maybe both of them. So I could write two smaller equations to figure that out. X plus 1 is equal to 0, and x minus 4 is equal to 0. And in this case, x would be equal to a negative 1, and in this case, x would be equal to a positive 4. Now, let me just give you a heads up. You may or may not remember this phrase, extraneous solutions. Extraneous solutions normally arise from squaring an equation, both sides of an equation, or multiplying or dividing by the letter, all right? You should, if you do any kind of extensive sort of technique here, and this was kind of involved, check the solutions in the original equation, and as long as you don't get anything funny, that you get some different number on the left side than on the right side comparably, all right, they're okay. All right, if you get two different answers, like if I put -1 in here, the number here should be 4. All right, let's test it real quick. All right. Here, any base log. All right, log of 3, and I'm going to put in this solution, -1. Shoot. -1. If my calculations are correct, then this should be equal to 4. And I should press this button, not that one. There's an error. Okay. Let's see. Oh, this is the wrong problem. That was a different problem. Of course it's 4. I'm a dummy. Sorry. Not that one. Alright. This one. Alright. -1 here. I'm going to stick a -1 here. Since that's what I figured out what x is. Alright. -1 squared is +1. Alright. +1 with a negative attached to it as an afterthought becomes e to the -1 on the left side. If I stick -1 here, alright, then this becomes +3. +3 minus 4 is still -1. So yes, that's a legitimate answer. If you checked 4 now in this equation, you will see that they match the end result as well. All right, well, you would end up with the z -16 on the left and e -16 on the right. So it would be also a legitimate answer. Just be careful. All of the time. Okay. Yeah, getting nearing the end here. Okay. Moving on. Look at that. Everything erases except blue. Why? Why is blue being such a jerk today? I need a clue. I need a blue clue. Right. My sister would be pleased with that reference. She's not here. Go away! No! So much effort to do that. Never show these videos to your family. Wow, you really are losing your mind. Yeah. Yeah, true. Let's see, alright, I'm gonna add desperation. I'm gonna try that fluid that came for whiteboard care. This is a whiteboard, it's acrylic plastic, but hey. No, that doesn't work. Only brute force works unless you use the alcohol. I hate using up all of my product. Go away! That's so terrible today. Alright. If I stripped it, maybe that's it. Maybe the alcohol is so harsh that it's taking some kind of veneer off this. Yeah, watch this. This is dry, right? Yeah. Much better, right? Look how easy that is. That's crazy. I'm running out of alcohol. At this rate, I'm not going to have any left. All right. Moving on. Sorry again for the intermission. All right. suppose that you started with this. Right, equals 42. Again, decide, are you working with an exponential equation to start with, or is it working with a logarithmic equation? I would say that this is exponential because there is a variable that is an x, all right, and there's no log here. All right? So we might eventually try to convert it to a logarithmic equation. Right? Before we do that, we're going to still perform the usual techniques from algebra, which is to isolate the variable. That's still true. The old techniques are still useful. To whatever extent that you can. All right, so if 3 is being multiplied here, and you want to just try to get that as far away from the variable as possible, putting it on the opposite side, do the opposite of multiplying by 3, which is namely dividing by 3. And if you did it here, you know you're obligated to do it to the opposite side for the sake of balancing. Okay, the 3's cancel. 2 to the x is equal to the quotient of 42 over 3. As long as it is divisible, you get a nice answer, not something that is a mixed number or decimal. Then I would perform the division. 3 goes into 4 roughly once with 1 left over, and 3 goes into 12 exactly 4 times, so 14. Cool. All right. Still try to pull tricks. If it is possible to convert this into something that is a base 2, I would. All right. Unfortunately, there is no base 2 that would produce 14. All right. So we can't do that. So what we're going to do at this point is convert from the exponential equation into a logarithmic equation. Okay. There's several ways to do it. I'll show you the way that was intuitive to myself, and then I think it's interesting. I want to show you what the book suggests to do. Your book suggests, well, if you're going to apply a log to both sides, all right, it doesn't have to be base 10. It's not wrong if you do. All right, you could make it any base. All right. Apply a log to both sides. But if you're trying to induce some kind of a cancellation effect, all right, use the same base. Because then you could take advantage of the inverse properties. Right? So for example, if this is a base 2, then if you take log base 2 of this argument, it would be to your advantage. Right? You know there's going to be a cancellation effect here. Right? Just make sure to do it to both sides. Remember, you can get away with murder in math as long as you're consistent that way. So, according to the power rule, if you have an exponent here, you can just write it as a coefficient, right? If you have the same bases, right, inverses, right, would produce 1, right? So this is really 1 times the coefficient up in the front, which is really just x, right? And therefore you're left with just this on the opposite side. The log of base 2 of 14, okay? If they ask you again to enter it into your calculator to give you a decimal equivalent, this is an exact answer. I would say that this is arguably best because this is exact. But if they wanted you to give a decimal, you would employ your calculator. So again, here's a quick way to do that, provided the software is up to date. Quit. Clear. All right. Now, you could, the fastest way to go about it is hit alpha and then window. And this little menu pops up. And you notice choice 5 is log base. That's any base. Oh, geez. 5. It has an intuitive place to put the 2 and an intuitive place to put the argument of 14. 2, 14. Okay. So what we got produces this decimal, 3.8073, whatever it is. You could say that this is approximately 3.807, right? If they want a decimal as an answer. Here's an alternative way. Again, I don't want to drive you nuts, but just bear in mind, you have options. It's the kind of thing that you have to save in the back of your head, and don't feel bad about it either. All right? If you went about it a different way. All right? Same problem. Let's say that you didn't employ the same base log to take advantage of inverse properties. Let's just say that at this point, you just took the log of this side and the log of this side, in which case it would be base 10, okay? The power rule would still say, well, if you have an exponent here, you could write it up in the front as a coefficient. That's the power rule. All right. And then you have the variable isolated, or you could go about the process of isolating the variable. This is what you have established. Okay. And now, if this is x on more or less the normal tier, right, you can move this factor that just coincidentally happens to be a log, right, over to the opposite side by performing opposite operations. What is the opposite of multiplying always? Dividing, right? And then you would do it here and here. And these would cancel, whatever they are as a decimal. And then look what you end up with. This would be x is equal to log of 14 over the log of 2. And that may not seem spectacular, but remember what we started with, right? The change of base formula, right? You can change this into basically this, all right? What was the end result here via change of base formula. It's just the change of base formula in reverse, all right? Normally you start with something like this, where you have a base, and any argument, and you write it like that. But this would produce this, argument of 14, base of 2. Same answer. Right. There is, as is often the case in math, more than one way to do something. So whichever way you go about it to start with, do not feel bad or be apologetic about it, right? If you get to the same result, fine. All right, just be aware, ultimately, you have options and maybe one way is more efficient than the other. You only know if you try. Okay. Let's do a complicated one. Clean enough? Yeah, I suppose so. Okay. Here you have e to the x plus 5 is equal to 60. Alright, again, I would argue this is an exponential equation. There's an obvious base here and an obvious exponent. So you will ultimately convert this to a log equation if it is convenient to do so. Still, you are going to try to isolate whatever you can. And that employs the old techniques of algebra. So, you should probably avoid using blue in general. You could use green. Move the 5. The opposite of adding 5 is to subtract 5 for the sake of moving it. There's a cancellation effect. E to the x is equal to 55. Okay, Now at this point, there's really nothing much, there's not much to it. You're going to, if you have a base E, all right, apply a natural log, all right? So if you apply a natural log here, do it to both sides. It is more or less going to be a cancellation effect. And the result is that you're going to get X, all right? You could employ the power rule first to justify that this would be up in front. But, and I did illustrate this on the handout, so I'll just refer to this one last time. When you have the natural log of E, you have 1. That is the result. They're inverses. So the result is just wherever the natural log of 5 is. 55, right? Again, if your calculator asks you, you can just plug this in. You'll get a decimal that's something like 4.007 something. Okay. I'll do another one underneath this here. Multiple step 2 to the 3 times 3 to the 2x minus 5 minus 4 equals 11. Do not be intimidated. All right, just proceed with this strategy. Identify what type you have. Exponential to start with, or is it logarithmic? You don't see the word log in here at all. It's exponential. We might eventually do this. All right, but what we're going to do first is try to isolate the variable in the traditional way. So we'll do the easy thing first. Reluctantly, I'm using blue here. Start by moving the little things that you can around. Addition or subtraction is usually what you do first when you're trying to manipulate an equation. That is to move it from here to here via opposite operations. There's a cancellation effect. That means that what you end up with in this case is the same 2 times the quantity 3 to the 2x minus 5, but it will be equal to 15 in this case. Okay, still there is this coefficient of 2 here. So if you want to, for the sake of isolating the variable to the degree that you can, do the opposite of multiplying by 2, which is to divide by 2. There's a cancellation effect, and if you did it here, do it here. 2, all right. I would do the division if it is divisible, that is if you get a nice answer, a whole number. It's not gonna work in this case. You will get 7.5, which is, it terminates, so I mean, arguably you can do it. 7.5. But now you have this. I'll put it up here. Green is misbehaving now, okay. Green and blue, maybe I should just write in red. Okay. We have this now. We have 3 that's left over as a base with the exponent, weirdly, of 2x minus 5. I'm just going to isolate it to draw your attention to it. These pieces, 2x and minus 5, are all, they're all the actual exponent here. And then there's this. If I reduced it as a terminating decimal, fine. Now you have this. Okay, we're ready to convert it now. All right. Again, it doesn't matter if you use log 10, base 10, or the natural log, which would be base e, but the trick that is suggested is to do this, all right? Use log with same base. So if you see the base is 3 here, and let's say that we apply log of base 3 to this argument here. And then if you've done it on this side, you're obligated at this point. do log of base 3 to the argument 7.5, right? Reason being, the end result is going to be just 2x minus 5 down here. How come? The power rule, or you could say that it's inverse property rule. All right, anyhow, you end up with this. 2x minus 5 is equal to the log of base 3 of 7.5. All right, we'll do a little more rearranging. And even though you get something that's a little bit more complicated than what you had seen to this point, it's still correct. So we're still going to pull our algebraic techniques. Move 5 by adding 5. It really can't be combined with anything because they're not like terms. This is a constant and that's a logarithm. But it's manipulating just by moving stuff around. So we have now the log of base 3 of the argument 7.5 plus 5. And the last thing is 2 divided by 2. So, although this is kind of ugly, the end result, this is legit. That would be your answer. Okay. Which, if you plugged it into your calculator, you get about 3.4 as a decimal. Okay. Now we're going to shift gears just a little bit. The thing that you're going to see now is an exponential equation, but you can employ older techniques to get through it. I'm going to bring back the subject of U substitution. This is dreadful today. Okay. Much easier that is. You have something that is a quadratic exponential equation. All right. It would look something like this. E to the 2x minus 3e to the x plus 2 is equal to 0. Can you try to factor something like this since it already happens to be set equal to 0? That's the overarching sort of technique that you want to use. You want to still ultimately factor, right? Well, maybe first set something equal to 0 if it isn't, then attempt to factor, then take advantage of the 0 product rule. Right? If you can, right? Those old algebraic techniques would be great for this. However, it's the factoring part that might be a little tricky. So as a side note, what you could try for the sake of factoring is U substitution. Essentially, U substitution is replacing ugly, complicated expressions with just the letter U. All right? Okay. You have everything else here. You have something that's kind of a polynomial. It's not by definition a polynomial, but it's sort of polynomial-esque, if you will. It's a trinomial. I'm going to use this word s because it isn't technically set equal to 0, all right? And it's in descending order. And the first term's degree is double second term degree. And one other thing, the last term is a constant. Right. So if you have this situation where you have something that's kind of trinomial, it's 3 terms. It's already set equal to 0, or you manipulated it as such. It's descending, which means that the exponents would be going down. Right? And this is the really important part. The degree of the first term, all right, is double the degree of the second term. All right? It's just times 2, so it's obvious. There are some problems that are more complicated than this, that it's 4 here and 2 there, but they would be still double, right? So it's the work. And the last term is a constant, it's just regular 2. What you're going to do is basically take the middle term that is the e to the x portion, and just call it u, right? You're going to disguise the problem just to get through the factoring, basically. So what you're going to end up with is this. You're going to have minus 3 here, and you have plus 2 here, and this is going to still be set equal to 0. But 2 things are going to change, all right? This, I'm going to, e to the x, I'm going to call u instead. And that means that since this is double that, all right, that this is going to be u squared. All right, if you're concerned about the minutia of this, and I wouldn't blame you, here's why. If ex is really u, and I take ex and I square it, now that's visible from far away, a little 2 there, then that's just making u squared, because e to the x is u. They're the same, right? Remember, the power rule for exponents would have me multiply 2x. Okay, anyhow, when you see something in this form, even though it's not the usual letter of x down here, it's some other letter, it's much easier to factor. So, you can go directly to what it will be. A binomial, sitting next to a binomial, we'll figure out the signs as an afterthought. If this is, look at me using blue, u squared, then the term that sits in the front of these is probably going to be u. Okay? If this is 2, 2 only has 2 factors, one in itself. So that would be a 2 and a 1. These are going from something smaller to something arguably larger, so there's only 2 things that could be involved here, adding or subtracting. What causes adding? In terms of sign combinations, both the same signs. And if you want it to be negative, they would both have to be negative. Simultaneously, a negative times a negative is a positive. A negative plus a negative is a bigger negative. All right. Anyhow, you have that. Now at this point, you can reverse the substitution. The only point of the substitution is just not to get bogged down when you're trying to establish what the factors are here. Okay? So we have u is really standing in place of e to the x. Right? Right? You could, if you want to, break this up into 2 equations, you know, according to the 0 product rule. right? Maybe this chunk is 0, maybe that chunk is 0, in which case it would be u minus 1 equals 0. And this would be u minus 2 is equal to 0. Or you could directly inject, all right, the EX at this point. I kind of leave it for dead last. All right. Anyhow, if you rearrange this bottom equation at u minus 1, what are you going to get? It would just involve moving the negative 1. So you would get u is equal to positive 1. And if you move this 2 from here to here, all right, you would get u is equal to positive 2. Right? And there isn't anything else but the substitution at that point. Replace your u with what it represents, really, e to the x. Right? E to the x. So this is really e to the x is equal to 1. And this is really e to the x is equal to 2. It's still not quite done because it's still an exponential equation, but we've manipulated it as far as we can go without algebraic techniques. Now we're going to take over with the applying logarithms to it. So I'll do that up here. But we have to do it twice, right? We have e to the x is equal to 1, and we have e to the x is equal to 2. The appropriate choice when you have an e is to take the natural log. Right. The result is that you're going to get x here. Because this by itself is just 1, it's just going to be, according to the power rule, you would put the x there. All right, you're going to get x. Right? And that means that it's going to be whatever the decimal equivalent is of the natural log of 1. Right? And in the other case, this is exactly the same thing. You're going to get an x times 1 because that's what the natural log of e is, their inverses. You're going to get x is equal to the natural log of 2. Right? These are your two answers. Now remember, for quadratics, expect two answers. Perhaps one of them is extraneous. You really should check it, you know. You get a dud. All right. But in this case, they're going to be fun. All right. The natural log of 1 is just 0. The natural log of 2 is this. It's about equal to 0.693. Yeah, I'll show you. If you took the natural log, clear please, the natural log of 2, there you have it, 0.293, pardon me, 0.693, I'm just rounding here. Okay. Right. The alternative, which I have neglected really to this point, would be to go back to the original equation. I'll just show you this one time. And graph it. Right, that's what that other part of that little diagram that I have for you that says, oh, well, you can graph this. That's what I'm talking about at this moment. And I'll show you really quickly. Here was the original equation. E to the 2x minus 3 e to the x plus 2 equals 0. All right. If you were to say, you don't really have significant sides here. You have y equals 0 on one side. So what you could do is just pretend that this is y. And plug this into your graphing calculator or graphing utility or whatever the app is that you have, all right? And then look for the zeros. All right, remember what zeros are. They're x-intercepts. If they're x-intercepts, that's figuring out what the x values would be when y is 0? What is x when y is 0? There'll be 2, right? And you can type that into your calculator. Firstly, by going through y equals, right? It's blanked out here. To type e is behind natural log. So you would have to hit second and then natural log, and it will show up as e here. And you'll use 2, and then this button x tau theta n is automatically x, and then just scroll out of it, and you're back on the regular tier. Minus, use this minus, and then use 3, and then the same sequence to get x. You have that, and then plus 2. All right. Now, is that correct? Looks like it is. I'm reading it backwards, unfortunately. Yes. All right. Now you would hit graph. I have to adjust the screen. If it's out of whack, do this. Hit zoom, which is more or less like the automatic, if you will. And try a couple of different things. Z standard would probably be sufficient. That's like a 10 by 10. But if you scroll down the list here, it might give you a more ideal picture. Zoom fit. I'm gonna go with that option. You get sort of a better picture. I don't really like that. It's taking its sweet time too. It's a little hard to read. I'm gonna zoom out. Look at my things here. So I'm gonna go to Z standard. That's a little bit better. There you go. Then maybe I'll zoom in now. When you hit zoom in, just be aware that when you choose the option, it doesn't do it automatically. You have to press enter twice. So enter and then go hit enter again, and it zooms in after you hit it the second time. There you see it crosses right at 2 places, 0, 0, and I'll bet you anything that is 2, 0. Now, a couple of things. If you hit trace, you could move the cursor over there, or what you can do is make an educated guess, right? Hit trace and then you can enter a value for this. If you hit 2 for x, then you get this for y. Natural log, yeah. And you hit 0. 0, 0. I want to know what that one is. I'm going to scoot over and see what it is. The problem with trace feature is that it's never really that precise, but here's y0 when your x value is this, right? The decimal, that's why. The decimal of 0.693 is what we calculated. This is just an estimate here. Now, there is a more precise way of doing this. If you engage calc feature, you hit second and then calc, you could ask it to find the zeros. This is a little tedious, all right, but I'm going to go through that process just this one time. It's going to ask you somewhat silly questions. It's going to say left bound and right bound. And left bound and right bound is basically moving the cursor so that it is no far to the left and no far to the right that you want to tell the calculator to look. It needs to be told. So left bound is, in this case, just underneath, I'm going to move with the keys here, just underneath where you suspect the x-intercept is, which would be right there, and go okay. And then it's going to be right bound, and you're going to scoot the cursor just above it, and you're going to go okay. And it's going to say, you want me to guess? And you go, yeah, I want you to guess. And then you hit enter, and then it spits out the result, 0.693 when y is equal to 0, which is exactly what we had calculated. Okay, the two x values, 0 because of the natural log of 1, and 0.693 because of the natural log of 2. Okay. Okay. All right, how are we on time? 2 minutes, 2 hours. All right, I swear we're coming to the end. I've been doing a lot of things that they start out exponential and we convert them to log. Let's do it the other way. be so mad at me and used to bully alcohol. As if by magic, look how fast that is by comparison, right? It's like I should be selling this stuff. It's like the Shane Wow. I'll get a headset, and be like, you need this product! Or no. It's just rubbing alcohol as well. Meanwhile, it works better than the stuff that came with the markers. We'll figure. It's just a pain in the neck to have to do it sometimes at a time. Okay. Moving on. Alright. We'll do a couple of problems that start as a log equation, and we will convert them to an exponential equation eventually. We may have to employ some other techniques in the process, but this is the basic gist of it. All right. If you are given, right, a log base e, which is what ln is, all right, then when you're converting to exponential form, right, you're basically going to raise that to an e. Just make sure that you do it on both sides of an equals. If you have a log in general, that's just log, which is understood as being log base 10, right, then it would be practical to raise it to a 10, or as a base 10 here. All right, just make sure that you do it on opposite sides of equals. In theory, whatever the bases of the log, log base, that sounds like some kind of like a video game slang from back in the day. Go back to log base, I imagine Lincoln Logs for some reason. All our base belong to us. There was some old weird mistranslation from a game back in the day. All your base all belong to us. Anyhow, whatever the base is, right, that's what you're going to raise it to, for the sake of taking advantage of the inverse property. Okay. So, if you had this as an example, the natural log of x is equal to 3. All right. Then if you do this, and you would have to do it to both sides, the effect is that since these are inverses, the argument is now isolated. All right. And then you just have e to the third. Okay. If you had this instead, something more glorious here. Log 3 of the argument 5x minus 1. And let's see, this is equal to log 3x plus 7. Okay. We have logarithms that are on opposite sides of equals, right? So what we probably are going to do is acknowledge the fact that these are already the same bases. So that means that they are 1 to 1, which means that we only have to pay attention to the arguments then. It's really 5x minus 1 is equal to x plus 7. And that's an algebraic equation that we can manipulate, right? So maybe move the 1 here by adding. They cancel. 5x is left over is equal to x plus 8. If I've done that, then I will move the x via subtraction to here, and it's a 1x technically. Cancels. And what I end up with is 4x is equal to 8. The last thing would be to naturally divide by the coefficient of 4. See if that's legible. Good. 4 over 4. And then x would be equal to 2. In a case like that. Okay. glue is going to be stubborn now. Okay. Here's another one. Log base 6 of 3x plus 14 minus the log of 6, base 6 of 5, and then on the opposite side, I'll erase this to get it out of the way. I have an ant over here who's watching me. Okay. Don't eat my food. Okay. Don't crawl over my face too, anything like that. I'm talking to an ant on the wall here. Hello, fellow sentient being. Well, so presumably. Earthling, fellow Earthling, there we go. Don't crawl on my face when I'm sleeping. I hate that. Okay. 2x. Alright, perhaps eventually I could take advantage of 1-to-1 in this case, but what I need to do is simplify left side first. So, notice what you have here. Same bases, alright, so I can combine them into one, I can condense basically. And this is a subtraction, so what I'm going to use is the quotient rule. And this will condense down to the log of 6, and then the arguments of 3x plus 14 will be situated on top of 5. Meanwhile, this other side is still this, log of 6, 2x. Alright, now at this point, I could take advantage of the fact that they're opposite sides of equals. So they're an equation, and they are the same bases. This is base 6, base 6, base 6, so they are 1-to-1. Which means that I really only need to pay attention to the guts. Right, I have the arguments here and here. 3x plus 14 sitting on top of 5 is equal to 2x. There's a lot of manipulation that will have to occur now, all right? But the logs are now gone. All right. Let's see. So we'll start by moving 5. If it's understood that it's being divided here, to justify moving it from here to the opposite side is to do opposite operation. Times 5 and then times 5. These would cancel. That means that you end up with 3x plus 14 is equal to 10x. To do it in the least number of steps at this point, probably should move the 3 over to the opposite side via subtraction since it's a positive 3x. These are like terms, these would cancel. That means that 10 minus 3 would be what? 7x, and on the left side technically would be this leftover 14. Move 7 via division, x is equal to, coincidentally, 2 again. Okay. Yep. Okay. One more of these that are a little bit more genuinely doing this, which is what I set out to do. And then I'll give you an extraneous situation. Everything but blue. Okay. 2 log of the base 5 of 3x is equal to 4. Again, we're going to try in this case not to simplify. We can't compact this too much, but we can isolate the variable by performing old technique. If there is a coefficient of 2, all right, in theory you could reverse this and put this here via the power rule in reverse. I wouldn't. I would just simply divide by 2 here, divide by 2 here, and now we have this. The log of base 5 of 3x is equal to 4 divided by 2 is just 2. We have a log equation. We're going to convert it to an exponential equation. We're going to try, you could draw the jelly bean right off the bat. I'll do it 2 ways. Right? If you do what is suggested, and it is practical, right, which is to go, there's a log of 5 here, so if I want to employ the inverse property, it would be raising this to a 5, and then the opposite side also to a 5. And the effect would be that we would just be left with 3x. The argument 3x is equal to 5 times 5, which is 25, divided by 3, and you end up with this crummy number. X is equal to 25 over 3, whatever it is, right? It's a decimal, 8 point something, right? Otherwise, I would say just draw the jelly bean, you know, and read counterclockwise. This is the base, it will always be a base. This becomes the exponent. What's on the opposite side? 3x. It's the same equation. Right? This is more or less the justification for it. This is inverse property. Right? But converting from one type to another, that's the basic process. Now I keep mentioning extraneous solutions. So let me give you an example where you would have an extraneous solution. I don't know how the whole batch of blue becomes so much trouble for me. Okay. Here's an example of having extraneous solutions. Which again, extraneous solutions are not your fault. Solutions. I'm abbreviating it as they had taught me in chemistry class. Right, basically, bad answers, for lack of a better phrase. They're not your fault, they just arise from extensive manipulation of an equation. Right. Usually it's from squaring, all right, or moving a variable around. If you have this, the log of 5x plus the log of x minus 1 equals 2. All right, I'm going to combine whatever I can, is my sort of train of thought here. I'm going to simplify the left side. Taking into consideration these would be base 10s, I can combine these according to the product rule, which means that this would be one expression of log base 10. You could just ditch that, you don't have to write that. And these are the arguments. Since it's being added, it would be 5x times x minus 1. I'll use brackets. Okay. And the other side is still 2. Let's see. If you acknowledge that this is a base 10, then you could draw the jelly bean, and that would be maybe the fastest way to go about it, really. The jelly bean links the base to the opposite side, which is squared, and you read counterclockwise. This argument of 5x times x minus 1 is the opposite side. The legal justification for this would be to raise this to a 10 or raise this as a base 10 here to the logarithm, and they are inverses. So the result is that the guts here, 5x times x minus 1, is the left side. And then if you did that to this side of raising to 10, then the opposite side, you would have to do the exact same thing to balance. I like my jelly beans. They work. Anyhow, regardless of which way you did it, what do you end up with? You get 10 squared. So 10 squared is really 100. And that's equal to 5x times x minus 1. It's purely algebraic at this point. So I'm going to distribute 5x. You get 5x squared minus 5x. And then I'm going to try to pull techniques. Right? Although I skipped a couple of steps in my writing it out. Right? I perform the jelly bean, which is really the inverse property. And I'm going to now try to arrange basically as a quadratic equation set equal to 0 in descending order. Reason being, you know that if I do that, then I can take advantage of the zero product rule and then solve it. That means that if I do that at this point, I want to preserve this as being positive. I just think it makes it easier. Minus 100, I'm going to subtract 100 here. It's not like terms, but this is now officially 0 on one side. And I have this as 5x squared minus 5x minus 100. All right. If you can factor in the most basic technique, which is via the GCF, extracted from each of these things and put it on the outside, you should attempt to do that first. The GCF of numbers 5, 5, and 100, so that they are made of the greatest common factor of 5 itself. So I can therefore write that as an outermost sort of factor here. That would reduce this to just x squared, that would reduce this to just x, and that would reduce this to just 20. 5 times 20 being 100. All right. Now at this point, I could factor the trinomial that's left over. And we'll reluctantly use blue again. If it's x squared, it's going to be x and x. If it's 20, and I want the end result to be 1, consider your options. 1 and 20, 2 and 10, 4 and 5. The choice of those three pairs that I would go with is 4 and 5, because multiplied together they make 20, but subtracted they make 1. So 5 and 4, I want to make sure that the signs are correct, right? They're shrinking, so subtraction has to occur. I kind of knew that already. But what causes it? One of each sign causes subtraction. One positive thing, one negative thing. If you want the outcome to be negative, the larger magnitude has to be the negative. Okay. Now, at this point, you would consider zero product rule. Hope that's legible. Which says that, well, maybe this factor chunk is 0, maybe this factor chunk is 0. The 5 you don't have to worry about because it doesn't have a letter. But if you do consider that this perhaps is equal to 0, then you have this tiny equation here. If you consider if perhaps this is equal to 0, you similarly have this equation here. And what you get is this. X moved would be x is equal to negative 4. 5 moved would be x is equal to positive 5. Right? These potentially would be our answers. But it turns out, all right, that this one, when you check it, right? I just wrote on something. When you check this in the original equation, it produces nonsense as an answer. It's an extraneous solution. Only x5 works. And yeah, you do have to kind of check it, especially if they tell you. All right, where do these things, these bad answers come from? They come from extensive manipulation of an equation. It usually is from squaring something or multiplying or dividing by a letter, which you usually don't do. You usually just multiply or divide by a coefficient. Anyhow, if you've moved the letters around a lot, and we have because we applied, we converted from a logarithmic equation to an exponential one, all right, you really should check for this, all right? Another thing that you could do is, again, plug in the original equation into your graphing calculator, all right? And again, look for zeros, all right? Which means look for x-intercepts. What you will see is a curve that looks like this. This probably later. If you were to graph the original equation using a graphing utility or a calculator, let's just say instead of calling it 2 equals 2, you purposely arranged it. All right? You rearranged the original equation so that it was 0 on one side, in which case it would look like this. Log of the argument 5x plus the log of x minus 1, and then if it's positive 2 on the right side, when you've manipulated it, it becomes negative on the left side. Right? It was originally on the left. Right? Meaning it looked like this originally. If it is now 0 on the opposite side, right, you can, for the sake of graphing it, just say, well, let's just call it y, right, and type this into your calculator to graph it, right. What you'll see as a picture is this. It's not going to draw any asymptotes, all right, but what you will see is, remember our solutions, x is equal to negative 4 and x is equal to positive 5. It's going to cross the x-axis, which makes it an x-intercept, at the location of 5, 0, all right? Because of that outcome from factoring and 0 product rule, which means that there would be a dot here, all right? Because it's logarithms, it has this distinctive curve to it like this. That's the nature of those types of curves. Remember, exponential would be the other way. They are mirror images of one another. And it just so happens that it has an asymptote, right? Normally the asymptote is the y-axis, but because it's shifted over a little bit, I want to say that the asymptote would be running down where it should be x is 1 instead of 0. Right? Think of transformations. Anyhow, in general, right, there's an asymptote. In general, logarithms never have negative x's. Why? Because they come up against this boundary that is x is 0. You know, under normal circumstances, sure, it's shifted over a little bit in this case because it's transformed somewhat. All right, but it's transformed, it's shifted that way, right? In the positives, right? So if you get a negative x, right, this graph validates the reason why this is an extraneous solution, because it's a negative when it's not supposed to be. Okay. Here is the absolute last thing, an application finally, right? How to do a word problem, basically. Some of this information is old, right? You already technically have this, but the kind of word problem that you have in the homework, the textbook homework, pertains to finance. So let me just bring this up again for the sake of clarity and reference. I'm going to write this really quickly. I don't have any sense of who typed it, but I'm sorry. Here's an application. This is how you would do one of the word problems. Okay. Example, right? You invest $500 at an annual interest rate of 6.75%. Compounded, continuously. Okay. How long will it take for your investment to double? Now, a couple of sections ago, there was a formula that I gave you, and I feel inclined to sort of write that again here for reference. All right. It's this. This is for continuously compounded types of problems. All right. A of t, that is a function of time, is equal to this. A times e to the rt. All right, just to remind you again also what each of these things represent. This is an account value. All right, it's just written in the style of a function of time, all right, which means that this is time in years. Okay, this is an interest rate, but that really is the percent that's quoted to you. It's just the percent as a decimal. This A is the initial value quoted to you. And E is the number 2.71, right? A2, whatever it is, into infinity. Anyhow, you have all the information that you need just make sure that you use this formula for continuously compounded interest. All right? And tweak it ever so slightly. All right? What's the initial value? 500 is what you would put here for the initial value. E, you're not going to change. The interest rate of 6.75% as a pure decimal would be to divide by 100. The effect is that the decimal point scoots over towards the left, which means that this number here is 0.0675. All right. Then there's the little extra tweaking that we need to know. First of all, we're trying to solve this not for the account value so much as for how much time it's going to take to double. It's not explicitly stated, but what is 500 doubled? Right? 1,000 is what the value would have to be. Right? The bottom line is that you're working with this equation. 1,000 is equal to 500 times e to the 0.0675 times t. And if you want to solve for time, you have to get t on the regular tier, right? You have to move it from being in the position of an exponent to on the normal level, if you will. How so? Well, if we have an exponent, an exponential equation and it has a base e, we could take advantage of the inverse property, which is to use natural log, which is a log of base e. And that would bring the t and this number 0.0675 down on the more or less normal tier. All right. Before we do that, let's isolate. Let's get rid of this coefficient. All right. If it's being multiplied and you want to manipulate it to move it over here, divide by 500. Divide by 500. This will cancel out of existence. And now, because I need the space, let me put the work over here. All right. 1,000 divided by 500, 2 zeros, here's a mental math shortcut, is really the same as 10 divided by 5, which is just 2. That means that e to the 0.0675 t is equal to 2. And if I take the natural log of this and the natural log of this to balance, the effect is that this is going to be down here. The natural log of e is just 1, right? The power rule would have me put this down here as a coefficient. So it would be that number 0.0675 times 1 essentially, which is just this. Okay, t. And now you have that. Natural log of 2. The next thing is to move the coefficient of 0.0675 by dividing, since it's being multiplied. 675, cancellation effect, 0.0675. This is what time it would be. You would enter natural log of 2 divided by 0.0675, right? And since we're trying to figure out the time, you might round it to maybe 10th place, or something like that. What you end up with is like 10.27 something. So this is about 10.3 years to double. Okay? Alright, and that's it. Alright, that was long. Next week, we're going to do the last section for the semester. Alright, the last couple of sections. And that's it. Alright, then I'll begin making the final exam. Alright, which I think I'm probably going to end up just giving to you. Alright, just let you have it. I don't want you to get scared. I can't collect it, but I'm still obligated to give it to you, so I'm going to give it to you. Here, have it. And then, well, I'll probably try to shoot a video, right, that explains how to do each problem. Okay? It'll be easy grade. Right. All right, thank you guys. For homework, do section 3.3 and 3.4. All right. And again, if you find these diagrams helpful, use them as you're doing the problems. All right, so 3, 3, and 3, 4, all right, in your textbook assignments. All right, see you next Sunday.